Hello and welcome to the lesson 9-4 practice. Again, I don't typically record videos of the practice, but with rotations by far being one of the most complicated transformations there are, with all the different things inside that encompass a rotation, such as rotational symmetry and rotating around a point and degrees and angles and all those things, I thought it would be worthwhile to record a video of it. So I hope this helps your understanding of lesson 9-4. So number 16 says, describe the rotation that would move or map the arrow to these positions. So this is actually the arrow from lesson 9-3 practice. So go check out 9-3 practice if you haven't. So they want to know, it's currently pointing left and the tip of the arrow is located at 0.3. And they want to know what rotation we would need to perform so that it's pointing up with the tip at 4.7. Now, I'll be honest, this coordinate plane is not doing you any justice because our figure is actually going to run off the page. 4.7 is located up here. So that's why I'm going to hop on this other screen and hopefully make a little bit more sense for it. So here's the same arrow. So they want to know what rotation could I perform so that the tip of my arrow is located at 4.7, which will be, let me use a different color, which will be right here. So we know that a rotation is a rigid motion. So whatever size and shape this pre-image arrow is, the image is going to be the same size and shape. So to kind of simplify this a little bit, let's think. We do have to either rotate this direction, which would be clockwise, or truthfully, we could rotate a lot further in a counterclockwise motion. But regardless, we do have to move that direction. So let's simplify it a little bit. Think about the distance that the tip of the arrow is to the base of the arrow, the back end of the arrow. That is 4 units in length. So if the tip now needs to be at 4.7 up here, I know that the base of my arrow is going to be 4 units down. So I can actually go and finish this shape out because I know it's a rigid motion. So the base of my arrow is 1 unit. So there's 1 unit. And then the length of this rectangular part of my arrow is 2 units long. So I'll go up 2 units, go out, and then I have my arrow. So the question is, describe a rotation that takes the point to 4.7. Well, here's a point that did not seem to move, or this is actually the pivot point around what the arrow rotated in order to end up as what you see here in red. So this is actually our center of rotation, which is located at 4 on the X, 3 on the Y. Now, depending on which direction you go, we could either say this went a 90 degrees clockwise or this much longer circular arc, 270 counter. So we will say 90 degree clockwise, this is for A. Apologize, one moment. Sorry about that. Let's jump back into it. So we're going to say a 90 degrees clockwise rotation or 270 counterclockwise rotation about the point 4.3. And so we'll go ahead and add that to our page on lesson 9-4 practice. So A is a 90 degree clockwise or 270 counterclockwise about 4.3. Now let's look at B. B says pointing down with a tip at 0.3. So let's jump back to our other page with the coordinate plane and let's make sure that it's pointing down. And think about it, if it's currently pointing left, how would it need to point down? Well, we needed to rotate this direction. So we could either say that's a 90 degrees counterclockwise, or we could argue 270 clockwise. So we need it pointing down with the tip at 0, 3. So let's jump back to this other page. So for this one, they want it to be located pointing down and the tip of the arrow still at 0, 3. So one thing we should have seen in the lesson, for a point to not move, it has to be the center of the rotation. So for item B, if they're suggesting that the tip of the arrow is still at 0, 3, but the arrow is pointing down, this has to be the center of our rotation. So if it's pointing down and we know the length of our arrow from the tip to the back end is 4 units, we're going to go 4 units up. And so this is now going to be the back end of my arrow. And because I know it's a rigid motion, I can actually finish, I think I went too few points, 1, 2, 3, 4, all the way up here at 0, 7. So I'm going to finish drawing out my arrow. So again, how did I know the center of rotation was located at 0, 3? Because they're telling us that the tip of the arrow is still located at 0, 3. So in order for this blue arrow to turn and point down, still located at 0, 3, tip still located at 0, 3, we either need to go 90 degrees counter or 270 degrees clockwise. So item B, we're going to say 90 degrees counterclockwise or 270 clockwise about the point 0, 3. And that's again because they're telling us that the tip of our arrow remains at 0, 3. So points that are fixed under a rotation have to be the center of a rotation. So let's jump back to our page and add that answer, 90 degrees counterclockwise. So 90 degrees counterclockwise or 270 clock about the point 0, 3. So now let's examine part C. Let's use a different color here. So part C, they're asking us for it to be pointing up with the tip located at 3, 0, which would be right here. 3, 0 is located right there. So the fact that it has to be pointing up, we know if it's pointing left to be pointing up, it definitely has to go 90 degrees clockwise or potentially 270 counterclockwise. So let's go back to our other screen and see if we can figure out how to do this. So we know we need the image to be pointing up and the arrow to be located at, or the tip of the arrow located at 3, 0. So again, if we know it's going to be pointing up, we know the height of our arrow, if you will, is 4 units. So we can go and construct our arrow, 1, 2, 3, 4. So this is going to be the back end. So we'll kind of finish drawing it just simply because we know it's a rigid motion, even though that's a terrible drawing. Please don't laugh too hard about it. So here's the problem. On A, we saw this yellow point here. We saw that there was a fixed point under the rotation, and we knew that was the center of rotation. And then on B, we saw, or they told us that the tip of the arrow would remain at 0, 3, and so that was an obvious center of rotation. Well, if you notice now for part C, which is this arrow in green down here, there's no fixed point, or it's not as obvious to find that fixed point. So what we're going to do is figure out where the center of rotation is if the tip of our arrow is now located at 3, 0. One of the easiest ways to do that is by drawing a line connecting corresponding points. So we know, or we should know, that however far a point is from the center of rotation, it has to remain that same distance from the center of rotation. Well, if you look at this corresponding point, it's kind of hard to tell, like, what is exactly going on here with the center of rotation. In fact, even if we draw this line segment, it's really not making it very obvious how this figure rotated. How did this blue arrow rotate 90 degrees clockwise, but end up way down here? So let's go back to our page It says pointing up with the tip located at 3, 0. So let's think about that for a moment. So I want to move to this more clear screen here, and we see that the tip of the arrow should be located at 3, 0. So I'm just going to kind of draw it out just a little bit. So we know that if it's pointing left and now it's pointing up, there has to be a 90-degree rotation. So the trick here is to find out somewhere between these two corresponding points, the tip of the arrow, how do we create that 90-degree angle? Well, they give us a really good hint here using the y-axis and the x-axis. Here's that 90-degree angle. In fact, if we connect the tip of the arrow from the pre-image to the origin and from the tip of the arrow from our image, we actually find that 90-degree angle. And we can do that with all of these corresponding points. For example, on the back end here, if we connect this point to the center of rotation and connect it to its image point on the back end of our image, we still see that 90-degree angle. So the way we found that center of rotation when it wasn't on the pre-image or the image was looking for that angle of rotation. And the reason we knew the angle of rotation was 90 degrees is because it was originally pointing left and now it's pointing up. So for item C, we're going to say that if it's pointing left and then pointing up, it should have been a 90 degrees clockwise or 270 counterclockwise about the point 0, 0 or the origin. So now 17 takes a slightly different direction, pun intended, and it asks us to identify the direction of the arrow and the position of the tip of the arrow after these rotations. So now we're kind of changing the direction here, like I said, and trying to figure out what direction is the arrow going to be pointing and where is the tip of the arrow going to be after, for a 90 degrees counterclockwise rotation about the point 4, 3. So let's hop back to our other screen here. 90 degrees counterclockwise about the point 4, 3. So let's hop back to our other screen. Still the same arrow. But again, what we're really focusing on now is just the tip of the arrow. So we're saying that we're going to rotate this arrow, and primarily this point that we're going to focus on, 90 degrees counterclockwise about this point, which is actually on the back end. I'll use a different color, which is actually on the back end of our arrow. So there's two ways to handle this here, more of a mathematical side and more of a conceptual way. So if we're going to rotate 90 degrees clockwise, we're going to travel, or counterclockwise, we're actually going to travel the other direction. 90 degrees counterclockwise, we're going to travel this direction. So we know, or should hopefully know, that we are going to be pointing down. The arrow is going to be pointing down because we're traveling a 90 degrees counterclockwise. Well, like we said on 16, we know that a rotation is a rigid motion. So if the length of our arrow, or from the tip to this point, is 1, 2, 3, 4 units, that however far a point is from the center of rotation, that's how far it has to remain after the rotation. So if we know that we're going to go 90 degrees counterclockwise and end up somewhere down here, if our tip of our arrow is 4 units from the center of rotation, then it has to remain 4 units from the center of rotation down. So that would actually put our point right here, the tip of our arrow located at 4, -1. And we don't necessarily have to draw the rest of the arrow because all they're asking us to do is figure out what the tip is. So our arrow will be facing down, and it'll be the tip of the arrow will be located at 4, -1. So let's go add that answer and see what's next for us. Let's add it with, I guess I'll use red. So for 17A, losing some room here. For 17A, we said it was going to be pointing down and located at 4, -1. Now let's look at item B. B says we're going to rotate 180 degrees about the point 2, 3. So let's go back to our other screen and see what that looks like. So we're going to rotate 180 degrees about the point 2, 3, which is located right here. 2, 3 is located right here. So we're going to rotate our entire figure, but primarily focusing on the tip of our arrow, 180 degrees about 0.23. Again, however far a pre-image point, again, the tip of our arrow, however far it is from the center of rotation, that's how far it has to remain after the rotation. Now notice they didn't specify 180 degrees counter or clockwise, because if we rotate 180 degrees period, we're going to end up in the same location. So for this tip to travel 180 degrees, we're going to go half of a circle. And however far it is from the center, which is 2 units to the left, it will end up 2 units to the right. So the tip of our arrow should now be pointing to the right and located at 4, positive 3. So B, our arrow should be pointing to the right, and the tip of it should be located at 4, positive 3. Let's jump back to our page and add that. So we're going to say to the right and located at 4, positive 3. Last but not least, for 17, we're going to look at C. It says 90 degrees clockwise about the point 2, 0. So 90 degrees clockwise about the point 2, 0. So we're taking the tip of our arrow, which is located at 0, 3, and we're going to rotate 90 degrees clockwise about the point 2, 0, which is right here. So this one's a little bit harder simply because the distance from the tip of our arrow is kind of at this diagonal. But again, if we're going to rotate 90 degrees clockwise, we are actually going to go this direction. And however far the pre-image is from the center of rotation, that's how far it has to remain. So let's compare these distances. We know that it has to be somewhere in this region over here, somewhere in this region, and it has to create a 90-degree angle. So I don't think that does it. So finding a little exploration here, let's think about maybe a more mathematical approach. So I think that actually yields a really good answer for it. But I'm not 100% sure. And in fact, some of you are like, how is he figuring out that the tip of my arrow rotating 90 degrees clockwise is going to end up here? So on item C, I'm going to show you the mathematical approach to be sure where a point ends up when the center of rotation is not the origin. So we have the point, or we'll call it A in this case, and we're trying to find where A prime is located. So A will be the tip of our arrow. So for item C, we have point A located at 0, 3. Anytime we perform a rotation around a point other than the origin, we use this kind of mathematical approach to find where the image is, again, when the center of rotation is not the origin. So the first step we're going to do is we're going to subtract the center of rotation, which in this example is 2, 0. What we're doing when we subtract 2, 0 is we're essentially moving that point to the origin, and then we're shifting the pre-image that we were trying to rotate, we're shifting it like we're shifting the center of rotation. So by subtracting 2, 0, by subtracting 2, 0, what we're really saying is we're going left 2. So think about that. I am taking the center of our rotation, which is located at 2, 0, and I'm moving it left 2, which will take us to the origin. Well, I have to move our arrow the same way, so I'm moving our arrow, primarily point A, I'm moving it 2 spaces to the left. So it's going to end up here for now. So just follow with me for a second. So 0 take away 2 is -2. 3 take away 0 is 3. So like I said, that point is located here just temporarily, and now the center of our rotation is located at the origin. Well, we still need to perform that 90-degree clockwise rotation. The function for a 90 degrees clockwise rotation is every point goes to, we swap x and y and change the sign of the x, or the second number. That's the way I look at it. We swap x and y and then change the sign of the second number after we swap. So what we're going to do now is take the point negative 2, 3, and we're going to use that function to rotate it 90 degrees clockwise. So negative 2, 3 will go to swap x and y, so it'll be 3, negative 2, and then change the sign of your second number, or what was the x, so it'll become a positive 2. So think about it. Now it's located at 3, positive 2. And hopefully you can see here that 90-degree rotation. Boom, there it is. But what do we have to do? Well, we shifted it left so that the center of rotation would be on the origin. Now we need to shift it right. And you might actually already be able to see that if we shift it to the right 2, we end up where I projected earlier. But the way to do that mathematically is we add the center of rotation back. So if we subtracted 2, 0 at the beginning, the last step we're going to do is we're going to add 2, 0 to the end, which will put us at 3, add 2 will be 5, 2 add 0 is 2, so A prime is located at 5, 2, which is what I projected. But that's what I did earlier was more conceptual, understanding what a 90 degrees clockwise rotation looks like. And this method over here is more mathematical, putting pen to the page, if you will. So a 90 degrees clockwise rotation, we should be pointing up, and the tip of the arrow should be located at 5, 2. So let's go back to our page and add that. So it should be pointing up, and the tip of the arrow located at 5, 2. We have 2 more to discuss. So 18 brings to light just another way to expound on what we saw on the previous page about rotational symmetry. It says, describe a figure that has an angle of rotational symmetry of 10 degrees. And so to explain that, I'm going to use some previous examples from the other page and maybe some more that you haven't thought about. So I'm going to jump over here, get to a new page. So imagine, if you would, rotational symmetry. We said on the previous page, to find rotational symmetry, you take 360 degrees, which is a full complete turn, and divide it by the number of lines of symmetry. So we're really trying to figure out, to find rotational symmetry, is we need to find the number of lines of symmetry a shape has. We use this term called regular, or sometimes irregular. But what we're really going to focus on is regular. A regular polygon is a polygon where all sides are the same length, all sides congruent, and all angles congruent. And think about it. For a shape to have any type of symmetry, it has to have sides and angles that are congruent, so that one side maps onto the other, one angle maps onto the other. So when we talk about a regular, let's say, pentagon, for example, we're talking about a 5-sided shape where all 5 sides are congruent and all 5 angles are congruent. So what that tells us is there should be 5 lines of symmetry, just like with a square, which is actually a regular quadrilateral if you think about it. It has 4 congruent sides, 4 congruent angles. A square actually has 4 lines of symmetry. We call one hamburger style, we call another hot dog, and then we can actually fold it along the diagonals. So, for example, if a square has 4 lines of symmetry, we take 360 divided by 4, we get a 90 degrees, which is our angle of rotational symmetry. But it all depends on, we needed to find the number of lines of symmetry. So a regular pentagon, if it has 5 lines of symmetry, its degree of rotational symmetry will be 5 goes into 36. It'd be 72 degrees. So its degree of rotational symmetry, or the angle of rotational symmetry, would be 72 degrees. I could rotate it every 72 degrees, and it would appear to map onto itself. So let's go look back at what we're trying to figure out with item 18. It says, describe a figure that has an angle of rotational symmetry that is 10 degrees. So think about it. If it all depends on the number of lines of symmetry, what we're really asking or trying to figure out is if a full turn is 360, we're trying to find the number of lines of symmetry so that it is a 10-degree angle of rotational symmetry. So to solve for this, there's multiple ways, but the easiest way is to multiply both sides by x, where this will cancel. We're left with 360 equal 10x. Divide both sides by 10. And we actually find x equals 36. So what are we finding here when we find x equals 36? Well, we're saying that a figure, a regular polygon, needs to have 36 lines of symmetry. Well, if this regular pentagon had 5 lines of symmetry and a regular hexagon, let me see if I can draw a regular hexagon. Well, if we say a regular hexagon actually has 6 lines of symmetry, 6 sides, 6 angles, well then a regular polygon with 36 lines of symmetry is a regular polygon with 36 sides. So what we're seeing is the connection of, especially for regular polygons, however many sides are congruent, that's more often than not how many lines of symmetry we'll have. And so if the end goal was to have a degree of rotational symmetry of 10 degrees, then we need 36 sides so that we could rotate it 10 degrees and it would appear to map onto itself. So let's go back and add that answer. So we're going to say for 18, a regular polygon, and that's important. We need all sides congruent, all angles congruent. A regular polygon with 36 sides. And I encourage you to go and look up what that's actually called for a regular polygon to have 36 sides. Last but not least, number 19, do you think it is possible for a figure to have an angle of rotational symmetry of 37 degrees? If so, describe the figure. If not, explain why not. So it all hinges on what we just figured out. We know on 18 that we wanted the angle of rotational symmetry to be 10 degrees, and we figured out it needed to have 36 sides, because if we divide 36 into 360, we get 10. So let's ask ourselves, really what we're asking ourselves, I'm actually going to jump on the other page. If we have a full turn of 360 degrees, and our end goal is to have a 37-degree angle of rotational symmetry, is there any number of lines of symmetry a shape could have such that x could divide into 360 and we get 37? So think about it. Is there any number we can divide into 360 and get 37? Another way to approach that, like we did earlier, is to take both sides and multiply by x so that this side cancels out. We get 360 equals 37x. And when you divide both sides by 37, and you actually put that in the calculator, you get a decimal. So there's actually not a whole number that divides into 360 such that we find 37 degrees for our angle of rotational symmetry. So let's go back and read the question again. Is it possible for a figure to have an angle of rotational symmetry of 37 degrees? It's not, because that would mean it needs to have 37 sides and 37 angles that are congruent, and there's no such shape that does that. So to explain that, 37 is not a factor. In other words, cannot divide evenly into 360, because 37 is not a factor of 360. it is not possible. So really, 18 and 19 are really just trying to deepen your understanding of what's really going on with these shapes and why or why not if they have rotational symmetry. And more importantly, finding the angle of rotational symmetry. So I hope this video helps. Always, as always, watch it, rewatch it, whatever you need to do to deepen your understanding. So thank you for watching.